Okay, so where are we now? So we motivated the discussion of statistical inference and estimation by bringing up this so-called decline effect, where the effect size of scientific results seems to be going down over time, and reproducibility is suffering. And so we gave some reasons for this: publication bias, mistakes and fraud, and this multiple hypothesis testing problem. And so we used these motivations, these scenarios, to bring up various topics and techniques. So we talked a little bit about basic statistical inference, where I just gave you an overview, and that's it. We talked about effect size. We brought up the specific term heteroscedasticity. For fraud detection, we brought up Binford's law. And then with multiple hypothesis testing, which is perhaps the most important part of the discussion, we talked about the family-wise error rate and the false discovery rate and gave correction procedures for both of these. Okay, and so this hopefully was a tour of not just some basic concepts, but also some, if not advanced, at least things that don't necessarily come up in a Stats 101 course. But I think it's pretty important for a data scientist to understand. In fact, as a data scientist, there's a view among statisticians that these topics are not very well understood. And in fact, they'll point to typical machine learning classes where understanding the population, understanding the various biases, understanding how to correct for the problems that can arise is not taught at all, and it's more of a blind application of algorithms. And so I think it's pretty important to sort of go over this choice of topics. Now, so what about big data? What changes? Well, so Brad Efron, who's a world-renowned statistician, describes it this way. It says classical statistics was fashioned for small problems, a few hundred data points at most, and just a few parameters. And the bottom line is that we've entered an era of massive scientific data collection with a demand for answers to large-scale inference problems that lie beyond the scope of classical statistics. And so suggests that something is changing in the era of big data. Now, what can go wrong here? Well, as we talked about, you can find spurious relationships in big data. And so this is a picture that I got from a colleague recently that was emailed to him, which is a plot that someone took the time to make. May or may not have been as a joke, but as you can see here, it says Internet Explorer versus the murder rate. Okay. And so this is the murders in the US in blue, along with the market share of Internet Explorer in the green, and the corresponding discussion that went along with this plot it was somewhat amusing, right? Talking about various theories for why the murder rate might be going up as Internet Explorer market share, or murder rate goes down as Internet Explorer market share also goes down. But the point here is that without some common sense, or without the application of understanding the scenario of the problem, you can make discoveries of this form. Okay. All right, and so other examples that have been talked about in the literature, again, brought up as bad examples. The number of police officers and the number of crimes. So why might these two things be correlated? Maybe police officers cause crimes. Well, no, probably because there's in densely populated areas there are both more police officers and there are more crimes. By the way, just to point out again, these authors here are not authors that made these claims. These are authors that brought up the mistake. Okay, amount of ice cream sold and deaths by drownings. Why would these things be correlated? Well, there's a seasonality, right? In the summertime, you sell more ice cream and more people go swimming. And then one is, stork sightings and population increase, used as, evidence that storks do indeed bring newborns to families. Well, again, in more densely populated areas, there's more people to actually see the storks, and so you get an increase in sightings. Okay, so these kind of procedures to remove bias and these procedures to understand the population you're sampling from and to understand the possibility of spurious correlations, these things are taught in statistics programs but are not typically taught in machine learning classes. Okay, so what does it have to do with big data? Well, there might be a view that there's the curse of big data, as Vincent Granville put it, is the fact that when you search for patterns in very, very large data sets with billions or trillions of data points and thousands of metrics, you are bound to identify coincidences that have no predictive power. And so the example he gives is to consider stock prices for some large number of companies over a 1 month period, and then you check for correlations in all pairs. And actually it doesn't stop there, because that would be over the exact same 1 month period, but you might want to account for lags. Perhaps the stock price of Google a few days later affects the stock price of smaller companies that depend on Google. Okay, and so now you're not just comparing every 500 squared. You're not just checking the pairwise correlation of these time series, but you're also checking the pairwise correlation among the slightly offset one. Okay, and so these are this cross correlation procedures. So very basic time series analysis is just to measure the correlation, and I just wanted to throw the formulas up here, where the covariance of two data sets is measured this way. All right, so you take the data point xi and subtract the mean of x and multiply that by yi minus the mean of y and add all that up, and that's the covariance. And then you divide the covariance by the standard deviation of each data set multiplied by each other, and so this gives you a correlation. Okay, so what does this experiment look like? Well, I generated this plot by running random walks for stock prices that start at $10. They all start at the same point, and at each step, which is an hour of simulated time, draw a sample from a normal distribution where the mean is the current stock price and the standard deviation is 1% of that current stock price. Okay, and this is not especially defensible, but you can see just sort of visually that it does generate stock price looking things, and you do get some variance here. All right, so clearly this is random. This plot shows the number of correlations at a level of 0.9. All right, that's a pretty strong correlation as a function of the number of stock prices tracked. So as I went up from 10 to 100, I didn't go all the way up to 500, which is what Vincent Granville described in the thought experiment. This is the number of spurious correlations you find. Okay, and this is also not doing the lagged cross correlation, right? This is just directly computing the correlation of these two time series across this month, and that's a pretty long period too, across a month. So what's the point? Well, big data gives more opportunities for spurious findings. Okay. Now, it's not all bad news. So how is big data different? Well, there's a notion of big P versus big N, where big P is sort of the number of columns and big N is the number of rows. And in this experiment we just did with the time series, this was sort of a big P scenario. We looked at an increasing number of companies, and then we looked at all possible correlation between them, so this was growing sort of quadratically. Okay. So the thing about big data, though, is that the marginal cost of increasing the number of records is essentially zero. It's gotten cheaper and cheaper and cheaper to collect data. Okay. Great. Now, that's very, very powerful, right? We want to increase the number of records, add statistical power, and helps us sort of, get lower and lower p-values. But it also amplifies bias. If you're collecting the wrong data, if you're looking at the wrong populations, you're going to make, so-called discoveries that are simply false. And so, for example, if you log all the clicks to your website, you have a very, very large data set, and you can very precisely model user behavior. But that would only model your current users, when your whole, perhaps the whole point of modeling user behavior is to try to attract new customers. Well, for example, if you have early adopters and your current user base is early adopters, you're only going to be modeling their behavior. You haven't actually sampled the population at large. Another example is mobile data, and this comes up in polling for, say, the presidential election. You're only sampling people that have cell phones, and this may or may not be the same population you want to be sampling. Okay, so this may ignore lower income groups or different age groups. Okay. Okay, you need to be careful at multiple hypothesis tests as well, as we pointed out. So there's a fantastic comic from XKCD that makes this point very, very clear, where they sort of demonstrate that green jelly beans cause acne, right? And the story here is that there's 20 different colors of jelly beans, and for a p-value of 0.05, we do 20 experiments, and sure enough, we find one of the colors indeed causes acne. But that would be expected purely by chance. And so I encourage you to look up that comic. And then the other comment I'll make that we will probably come back to is Nassim Taleb's black swan events. So this is things that are sort of inherently unpredictable, or the distribution of them does not follow a normal distribution, sort of a bell curve distribution, where the tails of the bell curve mean that extreme values become exponentially more rare. That's the sort of definition of the normal distribution. But in some cases, extreme values are not exponentially less common. They happen. Okay. And so the example that he uses in this case is that, you know, if a turkey was to model your behavior, it would get increasingly more confident that that you mean it no harm, and you mean it, you know, goodwill, right? Every day you come and feed the turkey, and every day you take care of it, and you look out for its well-being. But then on the, you know, day before Thanksgiving, it gets slaughtered, perhaps. Okay, and so that was Taleb's argument for black swan event. And black swan itself refers to the fact that people didn't believe black swans existed, and then found out that they did, and so it was an unexpected event. Okay, fine, and we'll talk more about that in some detail.